It's almost October. We started in August. We are now. We've kind of come a long way. There's a lot of notation now that we're using. But anyway, welcome everybody to Discrete Math. This is, here we go. This is going to be section 3.3. Got it. Nice. Yeah, by the way, my whole experiment with the other camera setup, we're abandoning that for now. That was way too small. I had way too less, not enough space at all. But today, we're doing section 3.3, and oh, there we go. Section 3.3. And I want to start off with talking about this whole, what it means for things to be equivalent thing, because I don't like the way I described it the other day. It felt long-winded and just convoluted. So I'm going to put that issue to bed right now. And the way we're going to talk about that is let's talk about what it means for things to be equal in like algebra, and then we're going to see a bunch of analogies. So for example, in algebra, if we define A, or I'll say X, if we define X to equal 1, then X equals X squared, right? Because 1 equals 1 squared. We good? I think we're good with that, right? But in general, does X equals X squared?
No.
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 But obviously not. For what was the question? What were you gonna say?
No, for negative X.
Oh, yeah, perfect. Exactly. Right. For no negative X's, we would use 2. Right. So for example, X equals X squared. No. X is not equal to X squared. In general, say, example, X equals 2. So the point is, like, if we actually define the variables here, and we actually define what X is, right, then X equals X squared. This just means evaluate left and right sides and see they're equal, right? So if we actually define an X, right, saying that the left side equals the right, like saying that we have an equality just means that the number the left side equals the number the right side equals, right? But in general, what this means is equality must hold for any values we plug in, right? So in algebra, right, if we're in general, if we don't define what X is, saying an equation's equal, saying it actually works, is saying that it works all the time. So an example, one of those is example in general, X minus 1 times X plus 1 does equal X squared minus 1. Because it works for all possible X, not just some X you plug in, like X equals X squared, all possible X. That makes sense, right? Good. So the point is that we have to be careful with thinking about things in general versus thinking about specific things. Because it's not always wrong that X equals X squared, but in general, X is not equal to X squared. All right. So we can see that in logic too. So in logic, right, P and Q does not equal P or Q in general, right? If you can C doesn't equal that in general, because, example, if P is true and Q is false, then P and Q is going to be true and false, which is false, while P or Q is going to be true or false, which is true. So true does not equal false. So in general, this equation doesn't hold, right? However, for specific P and Qs, like P equal true and Q equals true, right? Here, P and Q does equal P or Q, because this is true and true, which is true, and this is true or true, which is true. So even though this doesn't work in general, right? Like in general, this is not like a logic law we have, right? These are not equivalent expressions in general. Even though this work in general, sometimes it'll work if you have the right P's and Q's. All it's saying is that P and Q and P or Q are different. They are different statements, right? Just because they are different statements doesn't mean they can't sometimes doesn't mean they can't sometimes have the same value. For example, saying that like I like grilled cheese, right? And saying that the sun is made of hydrogen and helium, right? Those are both true statements. Do they have anything to do with each other? No, they're unrelated, right? For another person, maybe you don't like grilled cheese, but another sun is still going to be made of hydrogen and helium. So the point is, they're just unrelated. Sometimes they'll line up, sometimes they won't. They're just unrelated, different, right? That's what being not equivalent means in general. So sometimes they'll be the same though, sometimes they'll be different. Make sense? Okay, so now to bring this up to the big boy level with predicate logic, got ahead of myself, trying to combine a P into an R to make a PRAR. I misspelled logic. This is embarrassing. Okay, we're starting over. Predicate logic. I was never good at the spelling C's in school. I mean, spelling B's. See? So the point is, so predicate logic, what we just talked about last time is that the universal conditional is not equivalent to the universal converse. So what we showed last time is that for all x and d, P of x implies Q of x is not equivalent to for all x and d, Q of x implies P of x, right? These are just straight up different statements. Just like saying, I like grilled cheese and the sky is blue, right? They are just different things. Sometimes they're like saying X likes grilled cheese and the sky is blue. Sometimes someone likes grilled cheese and the sky is blue. Sometimes someone doesn't like grilled cheese and the sky, it's dark time. It's like dark time. This feels like a Game of Thrones or something. Sometimes it's nighttime and it's dark out and the sky is not blue. It's like black or whatever. So the point is, these are just different statements. So this equality, or not equality, this equivalence does not hold in general, right? So for example, right? Abe Lincoln never told a lie. If we go with that, what that means is that Abe Lincoln always meant what he said, right? And so if we make D the domain, things that Abe thought. And then we make P of X equivalent to Abe said X, and Q of X equal to Abe meant X, right? This statement right here is equivalent to what? What's the statement equivalent to in terms of what we defined here?
For all x and d, q of x implies p of x.
So here's where you have to be a little careful, right? Because I kind of said out of order specifically to have this conversation. So for
Okay.
all X and D, see, these are teaching moments. You think they just happened? No, they're made in a factory. They're made in the factory of my mind. The point is, so Abe Lincoln always meant what he said, right? If we're trying to deal with this statement, does P of X imply Q of X, and Q of X imply P of X? If we say Q of X implies P of X, what that means is that whatever Abe means, he says. But this isn't saying that he always said what he meant. This is saying he meant what he said, right? Saying that Abe Lincoln always meant what he said means that if he said it, he meant it. It doesn't mean if he meant it, he said it. Maybe there's a bunch of things out there that he meant, but he just kept his mouth shut. You see what I'm saying? This is only making a statement about things he said. Does that make sense?
Yes.
Awesome. So this thing for all PX, if Abe said it, then he meant it. Right? And let's just say true. Assume this. Right? So this is a universal conditional statement, right? But for all X and D, Q of X implies P of X does not have to be true, right? Abe does not need to say everything he means. Every thought that he believes, he doesn't have to say. So the point is, this statement and this statement are not the same. We found an example, right, of a domain with these predicates, right? We found an example of a D, a P of X, and a Q of X, where the conditional is not equivalent to the converse. So in general, right, these two statements are not equivalent, but sometimes they will be, right? I mean, for example, if we were to say, or first of all, does this make sense? It's a little confusing. Probably shouldn't use a Dr. I think I used a Dr. Seuss quote, but but yeah. Fourscore and 7 years ago. I wish I knew the Gettysburg Address all the way through. Our fellows by forth of this continent, new nation, conceived in liberty. Something. It goes on like that. It's only like 200 words. It's pretty crazy. Like one of those famous speeches of American history is like 3 minutes long. It's awesome. It gets straight to the point. I mean, I guess I can only name like 5 speeches in American history, but still. So for example, if we're looking for a specific particular case where they are equivalent, it's not saying it works in general, because where they are, we could say, let's say for all X in Benet said Washington's for all justice is a good one. That's right, where they want us about political parties. Who knew that would be an issue, right? Or, you know, you have Kennedy, where it's like we go to the moon and like this in this decade, not because it's easy, because it's hard. Oh, what a speech. I Have a Dream speech is a great American speech. That speech the president gives at Independence Day. Another great one. I was just gonna say that. Yes, exactly. That Independence Day. Thank you, Toru. Thank you. Someone who knows what I'm talking about. Probably the best one, honestly. But anyway, so if we say for all x in I have it written there. There we go. For all x in 13, 14, 15, x is even implies x is a multiple of 7. Is this true?
Yes.
Yeah, right? Looking at this particular domain, this is a true statement. Whenever x is even, it's got to be 14, so it's got to be a multiple of 7. This is true. How about for all x in 13, 14, 15, x is a multiple of 7 implies x is even.
Also true.
Also true. So in this particular case of this particular chosen domain, these particular chosen predicates, right? This and this, the universal conditional and its converse, have to be equivalent, right? They have to have the same truth value. But in general, it's not equivalent. That's the point. In general, it's not the same. Sometimes it will be. Sometimes they'll be the same. Sometimes they'll be different. You just can't always do the same. All right. I feel much better about that. How about you guys? Well, luckily, I feel good enough for all of us here. Which is how many people? What do we got today? Oh, we're not doing bad. I feel as good as like 7 people combined. All right, so moving on. Good.